find the Laplace transform of another commonly used function, the exponential, we do exactly the same process we did before. We're going to be looking for a function of s. It's going to be the transformed version of e to the at, and that, by the definition, is the integral from 0 to infinity of e to the minus st times e to the at. So this step here is applying the definition of the Laplace transform, and what we can do now is simplify and try to integrate. Let's be careful with our limits. First, we'll take the limit as b goes to infinity and then only integrate from 0 up to b. We can then join these two exponentials. If they're multiplied, then we can add their two powers. So we'll have e to the a minus s times t dt. And that we can simply integrate. Let's copy the limits first. We need those out front because they have not been evaluated yet. But the integral itself will be the same thing we had before. Divide by the new constant. There we are. And we'll evaluate that between b and 0. Copy the limit as b goes to infinity again. And then we can put in the limits of integration, the b and the 0. 1 over a minus s times e to the a minus s times b minus e to the 0. We're plugging in for t here. And then we can evaluate the limit as b gets larger and larger and larger. Now here we have two choices, we have two possibilities. This could either go to infinity if the exponential coefficient is positive, so we don't want that, we want something that converges. So we're going to ask that a minus s be less than 0, which is the same thing as saying s has to be bigger than a if we rearrange this. But that's okay, as long as there is a value for s for which this works, we're good. What that lets us do is replace this limit value with the value 0 as b gets larger and larger, which gives us 1 over a minus s times negative 1. So we could write that as negative 1 over a minus s, but that is kind of ugly. So what we usually do is multiply top and bottom by negative 1. That gives us 1 over negative a plus s, or more traditionally, 1 over s minus a. To summarize that, we would say the Laplace transform of an exponential is simply 1 over s minus a. And if we wanted to make that concrete, what's the Laplace transform of e to the minus 3t? Well, it would be 1 over s minus 3. Oh, careful with signs. This will be an issue throughout. We would have s minus the coefficient, which here would be negative 3. So we'd have 1 over s plus 3. And that's how we would use the transform on a function like an exponential. Take a look at a more complicated function, in some ways, the sine of kt. If we're looking for the transform of sine kt, what of course we need to do is evaluate the integral of e to the minus st times that function. Now this is a tricky integration by parts. If we do it by parts twice, we end up back at the same integral form. Notice if we did integration by parts once, we'd end up with a cosine. If we did it again, we end up with an integral with a sine in it again. And so what we're going to do is call this thing here I. We note that we see another I over here. And so when we go to integrate this, we can actually isolate it as I. There's one I on this side. If we bring this over to the other side, there will be a plus k squared over s squared. And then we'll have the rest of the term. Negative 1 over s, e to the minus st, sine of kt, minus k over s squared, e to the minus st cos of kt. So this is simply using a known formula for the integral of sine of kt times an exponential, only with the particular values, k in here, and the exponential being our Laplace transform kernel, e to the negative st. So what's next? Well, this integral didn't have limits on it, so what we have in terms of this I here is we add the limits of integration, we'll make it from 0 to infinity. Then when we do that to the integral that we're computing here, that becomes the Laplace transform of sine of kt. This I, with the addition of the limits of integration, will become the Laplace transform, because that's all that's missing from our original integral. We then keep the 1 plus k squared over s squared. Those don't involve t's. But what does happen, if we're going to integrate from 0 to infinity, and you remember how that works with integration by parts, we add the limits as limits of integration to any terms that popped out as part of the integration by parts. So we simply copy down this expression here. And last but not least, we recognize that we shouldn't be using infinite limits. So this is the idea that we have because we use the limits from 0 to infinity. But what we're going to need to do here is put a b in for our upper limit of integration and ask at the end, well, what happens as that value gets larger and larger? So what does that give us? What we're going to do is put in the value of b everywhere we see a t. Let's make that a little more clear here as well. These are values of t because our integration limit was t from 0 to infinity. And that will give us the limit as b goes to infinity, that gets copied, negative 1 over s e to the minus s times b sine of k times b. This t gets replaced by b minus k over s squared e to the minus sb cos of k times b minus what we get when we plug in 0. Now here we just use our rules of thumb. E to the 0 is 1, cos of 0 is 1, and sine of 0 is 0. So when we take this 0 value here and we put it into the sign, we're going to get nothing. When we take this 0 value and put it into this expression, we're going to get negative k over s squared times 1, which we can leave as simply negative k over s squared. So where does that leave us? Well, we still have to evaluate the limit as b approaches infinity. Again, we have this main ingredient, which is the negative exponential. And if s is positive, then what we're going to get is a negative exponential times a sine. You can use L'Hopital's rule or something else if you like, or you can simply recognize that this is getting smaller and smaller and smaller times a value that's between negative 1 and plus 1. What's going to happen when we multiply those? The whole thing's going to go to 0. And likewise, this term here is also going to go to 0. And this term here has no b's in it whatsoever, so it stays as is. So our next step would be to say that the Laplace transform of sine of kt times, let's keep this here, 1 plus k squared over s squared, that part there, is equal to two 0 terms. Well, that's not very interesting. But we have here still standing a k over s squared. Well, that's exactly what we're looking for. Well, almost. We have the Laplace transform of sine kt. We just have to move this to the other side, and we'll have what we're looking for. Copying over that formula, we want to solve for the Laplace transform of sine of kt. As an intermediate step, what we're going to do is take this part out and make it an s squared plus k squared over a common denominator of s squared. What that will do is make this transition easier as we move that term to the right-hand side. We'll have k over s squared. We're going to divide by this, which is the same as multiplying by the inverse or the reciprocal. And so there we get our s squareds canceling, and we end up with k over s squared plus k squared. So our final rule is that we can transform a sine function with any frequency in radians per second by replacing it with k s squared plus k squared. As an example, if we look for the Laplace transform of sine of 3t, we would get 3 over s squared plus 3 squared, or 3 over s squared plus 9. again, a function that started with t's in it, once we execute this transform, gives us a function back with s's only and constants.